All right, let's go through the four key RRSP features for this t-test. So we'll start off, as we always do, with the purpose. The purpose of a t-test is to compare two means. By the way, notice I just said t-test, not student's t-test. You don't have to say student every time, although many people prefer to add that in, again, to add a little bit of pizzazz to the name of the test. Oh, you may wonder why it's called a t-test. Well, really irrelevant, so don't worry about it. Back to the purpose, it's to compare two means, which can mean one of two things. Either we're comparing means of two separate populations, in which case we're going to use as null hypothesis the fact that one mean for one population is going to be equal to the mean for the other population, or it can be used to check if the mean of one population is equal to or different from a fixed number. So in that case, the null hypothesis will be of the form the mean is equal to some number. Okay, so we're going to have both of these ones, and you can, of course, you should be able to recognize that we're talking about the difference between a two sample test and a one sample test. What statistics are involved with the t-test? Well, remember I said this is a fairly easy, fairly simple procedure, and in fact all it uses are just sample means, sample standard deviations, and sample size. So mean, standard deviation, and sample size. Now, remember when we talked about the standard deviation among the descriptive statistics, and we talked about the fact that it is really not a very good descriptive statistic. Its meaning can be easily misinterpreted. It can be used in all kinds of wrong ways, and so on and so on. But I also mentioned at the time that the standard deviation is very useful in inferential statistics. This is it. This is where the standard deviation plays its big role, where it becomes really the hero of the situation. So mean, standard deviations, and sample size are used for this t-test. And what does it produce? It produces something called the t-statistic, not surprising, which is often reported. You're often going to see values for the t-statistics in research articles. However, really you don't need to look at it. Okay, so whatever information is in that number is really not that important. We can't really do much with it. As usual, it is always the p-value that counts and that we're going to focus our attention on. Let's keep going with the key features. Okay. So what are the requirements? This is the big issue. So for purpose and statistics, fairly straightforward. The requirements, this is where the troubles can occur. Okay, because this t-test has several requirements, some of which are pretty much present all the time, some of which are not. So let's see. First of all, probability sampling. Okay, this is a must for any statistical test if we want to do inference to the population, and it is true here as well. Also, independence of observations. The data that are collected for a t-test in order to figure out if two means are the same are supposed to be collected independently of each other. There is one exception, and that's where we're going to be using matched samples. Then, of course, the two pairs are supposed to be related to each other, right? So there is some relationship there. But otherwise, each observation should be collected and picked independently of any of the other ones. The other one is that this is a test that applies to continuous variables. Remember, we're comparing two means. Now, means could be compared also, or could be considered also for numerical variables which are not continuous. But the t-test requires and assumes that the variable is in fact continuous. When we looked at this issue of continuous variables, you may remember that I said that continuous variables are not really used in practice. They're a theoretical construct because in practice we always need to have some kind of a rounding. Therefore, what we're going to say is that the test requires a continuous variable, at least theoretical. In practice, we may end up with something which is not continuous, but the idea is, well, is it close enough to being continuous that we can assume it to be continuous? Either because theoretically it is continuous, or because the possible numerical values are so many that considering it as continuous is just a small approximation. Now, the next one is really important and often misunderstood or not checked. Okay, if two samples are compared, their variability should be the same. Remember that we're comparing averages, we're comparing means in particular, right? So what do the variables have to do with it? Well, a lot. So in fact, according to the technicalities of the t-test, the standard deviation should actually be the same in the two populations. So the population standard deviation. So of course, in the samples we may end up with different numbers, slightly different numbers, but they shouldn't be too different. Okay? We're going to see later what can be done when the variabilities are actually not equal. Okay? But the t-test per se requires the variabilities to be the same. Now, the other thing is that the variable is actually assumed to have a Bell distribution. So when we look at the histogram for the variable, and remember we're dealing with a continuous variable, we should be able to see a bell-shaped distribution. Now, bell-shaped again is a theoretical construct that doesn't exist in real life. You may want to review a little bit of what I say on the Bell distribution in chapter 9, which we skipped as far as this course is concerned. It's very technical, but you may want to have a look at it. But the point is that the t-test does require the original variable to have a Bell distribution. So, how are we going to check that? How should it be checked? Well, let's see. So how are we going to check that the variable actually has a bell-shaped distribution? Well, the simplest thing to do is to use the histogram, to look at the histogram. So let's say we have a look at the histogram and it looks something like this. Is it a true bell-shaped distribution? Well, we don't know. The bell-shaped distribution really is a very strict requirement, and this may not be it. Okay, but certainly this is what we're looking for. This would be an ideal kind of histogram, one that tells us, yes, go ahead, use the t-test, no problem. In real life, you're hardly ever going to see something like that. More likely, you're going to see something like this. Well, it sort of looks like a bell shape, but it has a little bit of a twist in it, and it's not quite exactly. It's a strange kind of a bell. That's okay. This is acceptable. It may not be ideal, but hey, this is life, and approximate things do happen. However, if the histogram starts looking like something like that, then you realize this is more like a staircase than a bell curve, and therefore this one is too skewed, too asymmetric, too far away from being a bell curve to be considered as acceptable for the t-test. Okay. There are other kinds of things that can go wrong. The histogram may look like this. Well, in this case, what we're really dealing with is two separate groups, aren't we? And so we shouldn't really be using this because it's what we call a bimodal kind of distribution. In order for it to be a bell-shaped distribution, it should have just one peak, not two like this one. The other thing is, remember, we're supposed to be dealing with a continuous variable, at least theoretically. So that means that if our histogram looks like this, with big gaps in between, that means that probably our variable is really not continuous. It is discrete. And in that case, again, we should maybe stay away from the t-test and use a different type. Or sometimes you're going to have something like this. Well, this is a histogram that doesn't really have any shape, let alone a bell shape. Okay, so in this case, again, using the t-test may not be a good idea because there is really no pattern on which we can base it. A different way to look at both the conditions on the variable, namely it has a Bell distribution, as well as the condition on the variability. Remember, we're assuming that the t-test requires that the two samples have the same variability, is by actually looking at the box plots. Remember box plots? Okay, so what we're going to do is we're going to compare the box plots for the two samples that we're comparing. So we're focusing on the variability, but I'll show you how the box plot can help in the bell-shaped issue as well. So ideally what we would like to see is something like this. Okay, so there are two groups and they look like they're coming from some kind of bell-shaped distribution. There is a good chunk in the middle and then some extended whiskers on both sides, and the two groups really are different because of their average. The one is shifted with respect to the other, but the variabilities in the two groups are roughly the same. So that's ideal. Again, ideal doesn't exist in practice, so we may have something that looks more like this. Not quite exactly the same, but fairly comparable. There is a little bit of asymmetry, there is a little bit of possible difference in the variability, but altogether not a big difference, and so this would be perfectly acceptable. However, if the two box plots look like this, now we have a problem. because the two groups have clearly different variability. One of them is much more compact, has much less variability than the other. So in this situation, we may want to be careful with the t-test. Certainly we don't want to use the t-test that comes from the sort of the standard t-test in this kind of situation. Another situation that can happen is this one. Okay, now first of all, notice that the variability in the two groups is actually different, not so much in the spread, but in how the quartiles are distributed, right? Notice that in the top one, the third quartile is very compact, very shrunk together, while in the second one it's the second quartile which is shrunk together. So the variability is not spread out in the same way in both of the groups. Okay, so that's one problem. The other problem is that this reveals a very strong asymmetry, which tells us that probably we don't even have a bell shape here. Okay, so the box plots can allow us at the same time to test for the equality of variability as well as the bell-shaped requirements.